So, yeah, hello and welcome to lecture number 19 of group theory. Let us keep continuing for now this video lectures. I don't know if you are watching or not, but okay, so last time we have seen unit 2, and this time what we are going to see is a new unit which is one of the most important topic in the theory of groups, that is Sylow theorem. Right, so let us begin. So first we define what is Sylow subgroup. Actually, we define after the existence, but let us I go this way. So what is the p-Sylow subgroup? Let G be a group. Let G be a group and P be a prime such that P power M divides order of G, but P power M plus 1 P power M plus 1 does not divide order of G for some integer M. Right? There is some M so that P power M divides order of G, but no higher power divides order of G. So P power M plus 1 and onwards, they do not divide order of G. Right? Then a subgroup of G of order P power M, highest prime power dividing order of G. So subgroup of order P power M, this is called a p-Sylow subgroup. This is called a p-Sylow subgroup of G. Right. So for example, if I consider a group of order 24, as we had seen, order of G equals to 24. So what is prime factorization? We have 8 into 3. Yes. So we have 2 power 3 divides order of G. So 8 divides order of G, but 2 power 4, 16 does not divide order of G, 24, which is 24. So a subgroup of G of order 8, 8 that is 2 cube, that is 8, is called a 2-Sylow subgroup of G. Is called a 2-Sylow subgroup of G. So for whatever the prime divides order of G, the highest power of that p raised to m, so that p raised to m plus 1 does not divide order of G, but p raised to m divides order of G, that power order, that order 2 raised to 3 here, that is called 2-Sylow subgroup. A subgroup of order 2 is not called a 2-Sylow subgroup. A subgroup of order 4 is also not called a 2-Sylow subgroup. Subgroup of order 8 here is called a 2-Sylow subgroup. And if we consider 3, then it is, so 3 also divides. So similarly, we can say that 3 power 1 divides order of G, 24. But 3 square, 9 does not divide order of G. 9 does not divide 24. So the order of a 3-Sylow subgroup, the order of a 3-Sylow subgroup of G is 3, 3 power 1. Right? If 9 divides, then we have to check 27 divides or not. If 27 does not divide, then it is 9. Here 9 does not divide, but 3 divides, so it is 3. So G has only two types of p-Sylow subgroups. So prime p equals to 2, it has a p-Sylow subgroup, 2-Sylow subgroup, which has order 8. For prime p equals to 3, it has a p-Sylow subgroup, 3-Sylow subgroup, which has order 3. Right. Similarly, you can take another example. Let us take order of G prime equals to 72. So 8 into 9. So 2 cube and 3 square. Yeah, so here 2 subgroup. So 2 subgroup has order, it will be 2 raised to 3, which is again 8 here. Right? 2 raised to 3 divides order of G dash, which is 72. But 2 raised to 4, 16 won't divide. Similarly, 3 subgroup of G dash is a subgroup of order, is a subgroup of G dash of order 3 square, highest power. 3 square divides 72, but 3 cube does not divide 72. So it is the highest one, right? Now the question is, what is the guarantee that a p-Sylow subgroup exists, right? So what is a guarantee that a p-Sylow subgroup always exists? P-Sylow subgroup, right? Existence of p-Sylow subgroup. So that is given by what is called Sylow's theorem. So there are, so it is, the existence is given by the existence of a p-Sylow subgroup, and that is first part. So actually this is called the main Sylow theorem, or the first Sylow theorem, or Sylow theorem. So there are three parts of Sylow theorem. The first one is also called just Sylow's theorem. Right? So let me write on a new page. So Sylow theorem. Sylow's theorems. So there are three parts. There is a first Sylow theorem, or first part of Sylow's theorem. There is a second Sylow theorem, or second part of Sylow theorem, which is also called second part, and third part. So third part of, or third Sylow theorem. Right? Now first Sylow theorem gives existence of a p-Sylow subgroup. Right? What second Sylow theorem says that two p-Sylow subgroups are conjugate. Third Sylow theorem says it gives the number of p-Sylow subgroups in G. Yes, and which is also used for applications. So second part and third part we are going to study later. Um, this also says, the second one also says that two p-Sylow subgroups are normal. So unique p-Sylow subgroup is normal. So good to have a chart like this. We'll again prepare something like this after we have done all these three theorems. A unique p-Sylow subgroup is normal. So all this will be very important results. And yes, in our course, in the first Sylow theorem, there are three proofs. There are very three different proofs. So the first proof is this. First proof is a combinatorial proof. So there are three proofs of the first part only. Second part and third part only have one proof each. But the first part has, the one is combinatorial proof. The another one is using class equation. And this one uses Cayley's theorem. Cayley's theorem and permutation groups. Something like this, Sn. So Sp power k. Yeah. And so this one is the most powerful. It's the most strongest result. So, of course, when I say strongest, it means the most strongest result, which we are going to do in this video. And the one using class equation. So this is similar to what we had seen earlier. Similar argument. Right? P divides order of G upon order of NA and so on. Similar argument to what we have seen earlier. In Cauchy's theorem for a general case, we have seen an argument and it is very similar. I'll make a video of this also. And this one is a combination of 2-3 results. It is not a direct proof. So 2-3 results collectively will give eventually the proof of Syllow's theorem. So Syllow's theorem, as I said, this gives the existence. So let us first give the existence of a p-Sylow subgroup. Right. So we are going to do this one, combinatorial proof, and which is the strongest one of them. So let me state the Syllow's theorem. Actual Syllow's theorem is this. Which is the first part of Syllow's theorem or the first Syllow's theorem, but it is known as just Syllow's theorem. Right, so the result is exactly same what we have defined in the definition, that it guarantees that there is a subgroup of order p power m. What is the definition of a p-Sylow subgroup? G is a, okay, when I say the group, I mean it's a finite group. So G is a finite group and P is a prime such that p power m for some integer m, p power m divides order of G, but p power m plus 1 does not divide order of G. Then the subgroup of G of order p power m is called a p-Sylow subgroup. What is the guarantee that highest prime power that it has a subgroup of that order? So that is given by Syllow's theorem. The statement is this: let J be a finite group and P be a prime, such that p power m divides order of G, but p power m plus 1 does not divide order of G for some integer m. For some integer m greater than or equals to 1, then G has a subgroup of order p power m. Then G has a subgroup of order p power m. That is, G has a p-Sylow subgroup. G has a p-Sylow subgroup. So actually, this is defined afterwards. What is a p-Sylow subgroup? That is actually defined afterwards, but I have defined it before only, and then we show that this exists. Otherwise, the result is proof first. Theorem પહેલા આવે કે આવું સબગ્રુપ મળે અને જો મળે છે ખબર છે then we know that it is called a, then we can say that it is called a p-Sylow subgroup, but I have defined it earlier itself. Um, okay, yeah, so it says that it has a subgroup of order p power m. So for example, if I have a group of order 24, as I said, so it says that it has a subgroup of order 8. So for example, a group of, by above theorem, by above theorem, uh, a group of order 24, which we write as this, has a subgroup of order if I take p equals to 2, we can say that it has subgroup of order 8, that is 2 cube. Also, it has a subgroup of order if I take p equals to 3, so then it has a subgroup of order 3. Right? So it has subgroup of order 3. It says that if I take whatever the primes are there, highest prime power order subgroup. So this is actual Sylow theorem, which is the first Sylow theorem, first part of Sylow theorem. And this is proved using class equation in whatever the book we are following by Herstein. So this is proved using class equation. This is what I have stated here, right? But we are going to study this in this video. We are going to study this proof. This I will make in the next video probably for you. And so we are going to see a stronger result. That stronger result is this, that not only it has a subgroup of order p power m, it has subgroup for all powers dividing this. So for example, here 2 cube divides this. So 2 raised to 1 divides 24, 2 square divides 24, 4 divides 24, 2 raised to 3, 8 also divides 24, 2 raised to 4 does not divide. So that theorem will say that it has subgroup of order 2, it has subgroup of order 4, it has subgroup of order 8 for all powers. બધા powers જેટલા powers divide કરે બધા powers નું હોય. So here it does not guarantee it has a subgroup of order 4. It does not guarantee, this theorem does not guarantee it has a subgroup of order 2. So this is actual Sylow theorem, but that is also called Sylow theorem. As also as a corollary, we have the same thing, same version. So theorem which we are going to prove is this, and this is also, let me write first Sylow theorem, first part. Or do not get confused with the first part. This is only first part, which is called Sylow's theorem. So it says let G be a finite group and P be a prime such that P power alpha divides order of G. P power alpha divides order of G. Alpha is any, for any integers, for some integer alpha. For some integer alpha, we are not saying that alpha is the highest one. We are not saying p power alpha plus 1 does not divide. P power alpha plus 1 divide kari sake. It may also divide. P power alpha plus 2 also may divide order of G. We are not saying that alpha is a maximum, right? So it has whatever power divides, it has subgroup of that order. Then G has a subgroup of order p power alpha. So this is even stronger because it says that group of order 24 has a subgroup of order 2 power 1, 2 power 2, 2 power 3. So subgroup of order 2, 4 and 8, as I said. So if we prove this, then of course the previous version follows. it has subgroup of all power. So highest power also definitely it will have a subgroup naturally. So that follows as a corollary, as a consequence of this result. So let us prove this one. So for the proof of this, we need a lemma. Let P be a prime. This is just a combinatorial argument, and it has no importance except that this one is used for once in the next theorem. So we just state it as lemma. We can as well show this computation, but then the proof will be lengthy in the proof of theorem. So in the book it is given in just one stretch. So we just state this one as lemma. So let P be a prime and M and alpha be natural numbers. I think yes, we need only this. R, M, alpha are natural numbers. If P power R divides M, but P power R plus 1 does not divide M, that is the maximum powers of P in M, which we can extract are P power R. P power R plus 1 does not divide P power R plus 1 does not divide M. Then P power R divides this binomial term, this coefficient. P power alpha M, choose P power alpha, right? N C K, N choose K, we know. But P power R plus 1 does not divide P power alpha M, choose P power alpha. So what it says? So it says that if there are R powers, maximum powers are coming from M, but R plus 1 is not coming, so maximum powers coming from M are R, then maximum powers of P which divides, that means which we can extract prime factorization in a bar Cartesian, which come from this is also when this is same P power alpha M, choose P power alpha. So maximum power here also this is R only, R plus 1 is not there. It's very simple result. There is nothing more complicated. Proof is easy. I leave as exercise just to see. Whenever there were seminars in the department, I used to give this as a seminar exercise. But let us consider an example. So I need more space. Let us take this. So if you don't understand, we have discussed this in class. But since this video I'm preparing independent of the class, maybe for other viewers. So let me take an example here. For example, take m equals to 20. Which is 2 square into 5, right? And p equals to 2. Then we know what is r. Then 2 square divides 20, but 2 cube does not divide 20. So the maximum powers of 2 coming from 20 is 2 square. So that is r equals to 2, right? P power r divides m. P power r plus 1 does not divide m, so r equals to 2. Then consider this, n choose k. So take alpha, any choice, any alpha. Right? Take any alpha. So let us take alpha equals to, let us say, 1. Let us try with alpha 1. Then p power alpha is nothing but 2 power 1. So then what is this? P power alpha m. P power alpha m, choose P power alpha. So that's it. So this will be 2 power 1 and m is 20 and 2 power 1. So this is 40 C2. So it is 40 factorial, 2 factorial, 40 minus 2 factorial, that is 38 factorial. So this is nothing but 40 into 39 upon 2, which is 20 into 39. So what are the powers of 2 dividing this? 20 into 39. So we can say that 2 square, 20, see here, 20, 2 square divides this 39, so 2 divided na correct. 2 square will divide p power alpha m, choose p power alpha, but 2 cube does not divide p power alpha m, choose p power alpha, right? Which is nothing but 40, choose 2. Or let us write like this: 2 into 20, choose, right? So that means if I have the same factor here, p power alpha in the same way, to maximum powers of prime p, which will divide this coefficient, binomial coefficient, will be coming from m. m માં જેટલા હશે એટલા જ હશે, exactly એટલા હશે. Yes, here you can see 2 square divides 20, but 2 cube does not divide 20. Then 2 square divides this, but 2 cube does not divide this. So here it is 2 power 1, 2 power 1. We can also take alpha equals to 3. If I take alpha equals to, in place of 1, if I take alpha equals to 3, then what will happen? Here we have 2 cube, here we have 2 cube. So here we will have 2 cube and 2 cube. So which will be 20 into 80. So that will be 160, choose 8. Then also it will be same. Even if we do this, then also it is same, right? 160, so this one you don't know what it will be, this 160 factorial upon 8 factorial and 152 factorial. It's very difficult to compute, but what this lemma says, because here m is 20, here it is same factor, so whatever the powers of p, whatever the powers p equals to 2 here will divide 20, that many powers, exactly that many powers will divide this. So 20 ને કેટલા divide કરે છે? 2 square, but 2 cube does not divide, so 2 square, 4 divides this, but 8 will not divide this, whatever this term will be. Even if you take alpha equals to 5, 10, 15, 100, whatever alpha you take, so it is not going to be any more than this, right? So if p power r divides m, but p power r plus 1 does not divide m, the same holds for this also. This is the fact which we are going to use somewhere once in the beginning in the next theorem, Syllow's theorem, the proof of Syllow's theorem. So it is stated as, so as a separate lemma, so that we can directly straight away use it without any confusion or without distracting ourselves from the main course of the proof. Oh, sorry. Yeah. So even if you take alpha equals to 2 or 3, this is going to be same. The thing is, here it should be p power alpha, here it should be p power alpha. Then whatever the powers of p will divide maximum powers. So maximum powers will depend on this only, m only. Okay, so now with this fact, let us prove this theorem. So what is the theorem? G is a finite group and P is a prime, so that P power alpha divides order of G for some alpha, then G has a subgroup of order P power alpha. We are not saying that alpha is the highest. Alpha plus 1 પણ divide કરે, પણ whatever alpha divides, એ બધા alpha P power alpha order ના subgroup હશે, right? Whatever the power divides. So 2 raised to 1 divides, it has a subgroup of order 2. 2 square divides, we are not saying that 2 cube may not divide. 2 cube પણ divide કરતું હશે. Then it has subgroup of order 2 square. If 2 cube divides, it has subgroup of order 2 cube and so on. Okay, whatever the powers divide. So if p power alpha divides order of G, what can we say about order of G? If A divides B, then we can write as this is the way we write B equals to AC for some C. Right? This is how we write B equals to AC for some C. So then order of G equals to p power alpha times m for some m. For some integer m. Again, what I am saying is highest power is not alpha. So there are more powers we can extract. So m upon powers હોઈ શકે p ના. So let p power r divides m, but p power r plus 1 does not divide m. Right? 24 order no group હોય. Order of G is 24. We want to show that it has subgroup of order 4. So p શું લેવાનું 2, and what we take alpha equals to 2. So 2 square p power alpha, it divides 24. Yes, we have to show that it's subgroup of order p power alpha. It has a subgroup of order p power alpha, that is 2 square. So what we write like this. So 24 ને કેવી રીતે લખવાનું? p power alpha times m. What will be m? બાકીનો ફેક્ટર છે 22 4 divides 24 તો બાકી શું વધે 6. So m will be 6. This is our m. Right? If we write like this, p power alpha and m. So that means કે 2 ના પાવર ખાલી 2 જ છે? No. The power of 2 is still here. હજી એક પાવર તો છે, 2 will still divide. So one can also extract 2. પછી તો કે 2 સ્ક્વેર અને 2 લીધું આપણે. હવે શું રહ્યું? તો કે હવે m માં તો પછી આ જ રહ્યું. Can we still extract 2? No. હવે તો m માં કેટલા પાવર્સ હતા? m માં ખાલી 2 ના 1 જ પાવર હતા. Right? So that means when I say p power alpha divides order of g, it is not the highest power. So that means order of g equals to p power alpha m. Because it is not highest, there may be some power. Highest હોઈ પણ શકે, ના પણ હોય. It may be highest, it may not be highest. There may be some power. If it is highest, then r is 0. અને હવે અહીંયા 3 લઈ લીધું ને, now this has become highest. Now if I take this as m, there are no powers. So 2 power 0 divides this. So r will become 0. I hope this is clear. Otherwise just repeat it. So m માં પણ p ના powers હોઈ શકે. Let us extract that. So suppose there are r powers. R is greater than equals to 0. It can be 0. Alpha જો highest હોય તો પછી એમાં m માંથી કાંઈ ના નીકળે. Right? So let us say that there are r powers of p in m. That means p power r divides, that is maximum. p power r divides, એને આપણે fix કરીએ. Suppose p power r divides m, and so let us say suppose p power r divides m, but p power r plus 1 does not divide m. એ r આપણે શોધી લઈએ, whatever the r is that we find, and fix it r. So for some r greater than equals to 0, r can be 0 also. If alpha is maximum, then r is 0, no problem. તો પછી m માં કોઈ પાવર ના મળે. So g માં કેટલા પાવર હશે p ના? p power alpha already we can see here, but m માં પણ હોઈ શકે. m માં maximum કેટલા છે? p power r. So that means then what we can say is that p power alpha plus r divides order of g. હવે આનાથી એક પણ વધારે ના કરે. p power alpha is clearly we have seen here. p power r is maximum coming from m. So maximum in g is p power alpha plus r. But we can say that p power alpha plus r plus 1 does not divide order of g. Right? Now we have extracted everything, whatever the powers. P power alpha was clearly outside. From m also we take p power r. R is a maximum. Then there cannot be any further powers. But we don't need this. We just observe this. So that p power alpha plus r divides order of g. Right? What we need is we need to produce a subgroup of order p power alpha. We want a subgroup of order p power alpha. So what I do is I take the collection of all subsets, not subgroups. I take the collection of all possible subsets. उसमें identity हो भी नहीं, कुछ भी है चलेगा. But I am taking just collection of all subsets of p power alpha elements. So let m be script m. So this curly m be the collection of, we want a subgroup of order p power alpha, but let us consider collection of all subsets of g having p power alpha elements. Right? Having exactly p power alpha elements. So what are the elements of m? Elements of m are subsets of g. So if I take capital M in script m, then m is a subset of g having p power alpha elements, having exactly, we are not saying it is subgroup. Subgroup and there are, because subgroup is a subset, but we don't want subgroup. We want to find, but we are taking a collection of all subsets having p power alpha elements. તો આવા કેટલા sets બને? What is the cardinality of m? Question is, what is the cardinality of m? Cardinality of script m. How many elements will be there? So if g has suppose 5 elements, suppose I have a set of 5 elements, a1, a2, a3, a4, a5. I'm not saying it's a group, otherwise you will say identity just for explaining. Suppose G has 5 elements. We want all subsets with 3 elements. So how many such subsets we can make? I can take A1, I can take A2, I can take A3. I can take A1, A2, I can take A4. I can take A1, A2, A5. All such combinations. Yeah. All such combinations. Our kitla banse. How many such subsets I can form? So there are 5 elements, and I choose 3. So we know this is 5 choose 3. 5C3, right? 5C3 is 5 factorial, 3 factorial, 2 factorial. This is 10, right? 5 into, so this is 5 into 4, 3 factorial get cancelled upon 2, so this is 10. So there are 10 such subsets of 3, having 3 elements. If I have a set of 5 elements, so see NC3, so that is why we have stated that lemma, because it was, this is where we are going to use the fact. Okay, so how many such, what is the cardinality of M? So I can write, then M has, this M has how many elements? Order G, choose p power alpha elements. Yes, G ની અંદર કેટલા elements છે? How many elements are there in G? Order of G. And we are taking subsets. We are forming all subsets having exactly p power alpha elements. So that is, this is nothing but, what is this? Order of G is here we have fixed p power alpha m. Right, so this is p power alpha m, p power alpha elements. Okay, so now see this has come just like above lemma. So how many powers will divide this? How many powers of p will divide this term? Exactly those powers which are coming from m, because here also it is p power alpha. Here also it is p power alpha. So how many powers maximum will divide this? They are coming from this m. Right? So by above lemma, since an m ma kitla powers se, m has this. P power r divides m, but p power r plus 1 does not divide m. This is the fact we use the lemma, so we have stated that as a lemma. So here also p power r divides this. So by above lemma, since p power r divides m, but p power r plus 1 does not divide m, by the above lemma, we can say that p power r divides p power alpha m, choose p power alpha, but p power r plus 1 does not divide p power alpha m, choose p power alpha. That is, what is this term? This is nothing but the number of elements in M. M માં કેવા છે? Subsets બનાવીએ. We are forming a subsets of G of p power alpha having exactly p power alpha elements. So how many such subsets we get? So we have total number of elements, we choose p power alpha. So total number of elements is p power alpha m, and we are choosing p power alpha. So this is, so M has so many subsets of G. So that is p power r plus 1 does not divide the order of M. P power r plus 1 does not divide order of M. So these are the some things which we want. So order of G is this, p power alpha m, where M has maximum r powers of p. This is also we want. This is, so G has how many powers? Alpha were already outside here, and M has r. So maximum this G has r. Then this is collection of all subsets having p power alpha elements. And by above lemma, this is also one of the fact we need. So we want this also. Right, our setup is done. Now as I said that there will be some baby exercises so that we divide this result into some steps. Right, so once this is done, we divide into 4 steps. Right, the first step, that is and we'll see the proof as a whole, then we'll expand all these steps. So first step is defining an equivalence relation. I'm writing like this for your understanding, otherwise the proof is not to be written like this. I'm just writing for our understanding. So equivalence relation on M. Define a relation. So this is for us to remember, so that once we know all these steps, then it's an easy verification. So you just need to remember these four steps. First one is equivalence relation. What is the relation given? So for, if I take two elements, so for I take M1 and M2 in M, right? What is M? M is a collection of all subsets of G having exactly p power alpha elements. Subsets, not subgroups. Again, so suppose I take M1 and M2. What are M1 and M2? M1 and M2 are subsets of G and both has p power alpha elements. So we define for them M1 is related to M2 if we can write M1 equals to M2G for some G in G. Right? The relation, two elements, two subsets having exactly p power alpha elements, two subsets of G belongs to M means they are subsets of G. Two subsets of G, we say that they are equivalent. M1 is equivalent to M2. If M1 can be written as M2G for some G in, it's like a coset. This is like a coset. M2G for some G in G. Now we want to show that this is an equivalence relation. Let us not distract ourselves from this proof. So we'll do this. We'll verify this verification later. Next is step 2. So step 2, we claim that p power r. So after equivalence relation, what comes? Equivalence class. So we now talk about equivalence class. So we say that p power r plus 1 does not divide order of the number of elements. So we say that there is an equivalence class M, equivalence class, let us denote by this, and some M, right, where M is an element of the script M, such that p power r plus 1 does not divide the number of elements in M, the number of elements in M. In this class. Now this I'll do for you. Anyway, I'll do all the steps, but this I can write right now. So what is so when we have equivalence class M, what is the number of elements in M? It is divided into, so right, આપણે આવું લખીએ ને, order of G equals to, when we have equivalence class, we have some elements here plus some elements here. So total number of students in the department is equals to students in the semester 1 for class 1 plus semester 2, semester 1 class 2, semester 3 class 1, and plus semester 3 class 2. So if it is an equivalence relation, what is the cardinality of script M? Cardinality શું થશે? તો કે number of elements in the class first class, number of elements in the second equivalence class, number of elements in the third equivalence class, and so on. So because the group is finite, M is finite, there are finitely many such equivalence classes. Now what happens if p power r plus 1 divides each and every term? So if p power r plus 1 divides this, if p power r plus 1 divides this order of this, if p power r plus 1 divides order of this, if p power r plus 1 divides each and every term, then p power r plus 1 divides their sum, which is nothing but it is nothing but here p power r plus 1, which divides the cardinality of script M, right? That means p power r plus 1 divides the number of elements in M. So here this is what we have. Yes, p power r plus 1 does not divide this. So that means p power r plus 1 does not divide the order of M. So if it does not divide order of M, so it should not divide this order of M, cardinality of M. That means it cannot divide all these terms. It cannot divide this, it cannot divide this. Is it clear? So what happens? We cannot say it does not divide all of them. It may divide some of them, but it cannot divide all of them. Okay, so that is a language, this thing. What I'm saying is that there is one such class, so that p power r plus 1 does not divide number of elements in this class. Because if p power r plus 1 divides number of elements in this class, p power r plus 1 divides number of elements in this class, and so on, and every class, then it divides the number of elements in M, which is not the case, right? So that means there is exactly one class. So here it is written, there is one equivalence class, let us call it M, such that p power r plus 1 does not divide number of elements in it. So here there will be some M, and any cardinality will p power r plus 1 will not divide this. Is it clear? I hope just repeat it once. It's a video. You can do it. So I write that argument. Right. Suppose what happens if suppose for each equivalence class M. Suppose for each we write the argument for this. For each equivalence class. For each equivalence class M, if p power r plus 1 divides the number of elements in M, then p power r plus 1 divides, because it's an equivalence relation on M, right? So if it divides each class of M, then it divides number of elements of M, divides the number of elements in script M. So it divides the number of elements in script M, but by above lemma it is not possible. So which is not possible? By above lemma. So that is where the above lemma is used, but what we have as discussed in star. But we have already discussed here. So what above lemma concludes is I have written here for understanding. So we can just refer to this as discussed. So hence the claim. So hence there is at least there exists at least one equivalence class. So there exists at least one equivalence class. एक तो मल्सेज class of M, let us say equivalence class M, such that p power r plus 1 does not divide p power r plus 1 does not divide, let us write like this, does not divide the number of elements of M, number of elements in M. How many elements are there in M? Whatever the elements, p power r plus 1 will not divide that. So okay, so this part is done. And yeah, so let us write, suppose M equals to M is equivalence class, and let us suppose M has class of M has all this M1 M2 up to, let us say, Mn. Suppose this is equivalence class, there are this many members, n members. So then what we have seen, then by above, p power r plus 1 is not dividing number of elements in M. So p power r plus 1 does not divide how many elements are there? Here we have n elements. So we say that p power r plus 1 does not divide n. So this is also what we are going to need. And also these are all equivalent. So what is the equivalence relation? M1 is equivalent to M2. M1 is equivalent to M3. All these are equivalent to each other because they belong to the same class. So that means one can be written as equivalence relation. What was the equivalence relation? Recall? Yeah. So one can be written as some another times some g, m1 equals to m2g, or m2 equals to m1 g inverse. This is equivalence relation which can be verified easily. Okay. So there is one class. So that means clearly by definition, of equivalence relation, so by the definition of equivalence relation, what we have, if I take g in G and mi in this class, and then uh, g in G and mi in this class, then what is mig? Mig is also mi times G. So that is also an element of this class only, because this will be either m1 or it will be m2, or up to it will be mn, because this is how equivalence relation is defined. As you can see, they are two equivalent if one can be written as m1 can be written as m2g, or one can be written as other m2 is equivalent to m1 if m2 equals to m1 g inverse. If m1 equals to m2g, then so because it is an equivalence relation, so they are, so that means this guy belongs to mig will belong to the same class. So this belongs to the class M, right? So this is our observation, and now we come to the step 3. We are interested in all those G for which, so define H equals to, right? So if I take M1G, so M1 is an element in this class. If I take M1G, either it is going to be M1 or it is going to be in the same class. So it is going to be M1, M2 or Mn. આટલામાંથી કંઈક હશે. But we are interested in all those G in G for which M1G equals to M1. M1 જ આવે એવા G we are interested in, right? So we are interested in all those G for which G in G such that M1, this is our H which we are looking for. P power alpha order nu we wanted group of subgroup of order P power alpha. This is how we are going to show eventually that this is subgroup. So M1G equals to M1. We are interested in only those G, right? Okay, so now is it non-empty? H, first of all, we have to show subgroup. We have to show that it is non-empty, right? So of course it is non-empty. Which element belongs to this? G is a group. Identity belongs to this. And what is M1 times identity? So M1E. What will be M1E? This will be like ME, so that M belongs to M1. So ME, because it is group, they are all elements of group. So this is nothing but M, such that M belongs to M1. So which is nothing but M1. So M1E equals to M1. So there is at least one element. So H is non-empty. And now we have to show that. So claim is show that it is a subgroup. H is a subgroup of G. So another baby exercise. What I say, very small exercise. We divided it into parts. So H is a subgroup. Let us keep some space for that and go for the next step. Now we are going to show that H has P power alpha elements. So let's define a map. So this is step number 4, final step, and then we are done. So define a map psi from this equivalence class. Define a map psi from the equivalence class M to HG such that G is in G by, how do we define? Psi of this equals to, so we want some element here such that and then we want to define a right coset of h in G. How do to define a right coset of h? I need some element G in G. ये क्याथी मळ्छे? So that should come from here only, right? Here is some element of M1, so not M1, equivalence class of this. I should get such an element which gives me G. As soon as I get G, I will form right coset HG. So G के રીતે મળશે? So what are the elements of M? M is nothing but it has n elements: M1, M2, M3, and up to Mn. There are n elements in this equivalence class. I can take M1. If I want M1, I can write this as M1E. So I have an element of group, so I can take HE. So M1E goes to HE. What if I take M2? તો પછી મારે M2E, but then HE. તો પછી બધા HE માં જ જશે. So this is not a correct way to define. But if I take, so then it is not HG, right? We want HG, exact same. So if I write M2, what I know, M2 is in the same class of M1. Same class માં આવે છે, that means M2 and M1. M2 is equivalent to M1. That means M2 can be written as M1 times G for some G, and that G I can write. Now if I want to take here M3, so M3, so for M3, I don't write M3, but I know M3 is equivalent to M1 because they are in all the same class. So M3 can be written as M1 and some G dash. So that G dash I'll form HG dash. So here I'll form HG. So if I write M5, M5 is equivalent to whatever the elements will be there. So that is the idea, right? So every element here is related to M1, right? Every student of your class, there is a CR. So you can talk to your class representative. So here also let us take representative as M1. You can take M2 also. કોઈ ફિક્સ નથી M1 ને CR બનાવો ને, કોઈ પણ CR બની શકે વોટ જેને વધારે મળે એને. But they are all equivalent because they are in the same class, right? So no one is special, but here we write every element is of the form M1G for some G. Every element here is of the form M1G. M1 is also of the form M1G where G equals to identity. M2 is equivalent to M1, therefore M2 equals to M1G for some G. M3 is equivalent to M1, so M3 can be written as M1G for some other G. So every element here I can write in general M1G. So as soon as I get G, I can write here HG, and for all M1G in this equivalence class. This is the map we have defined. Then our claim is size bijection. Our claim is size bijection. Right, so let us leave some space for the bijection, and then finally, if psi is a bijection, then what is the conclusion? What we get, that will prove our theorem. So what the conclusion we get is, if this is a bijection, there are two sets, so both will have same number of elements. So the number of elements in M is same as the number of right cosets of H in G. This is nothing but set of all right cosets. So how many elements are there in M? M માં કેટલા elements હતા? M we have fixed, right? Here, n elements were there. So that means then let us write then n equals to index of if we want to write one more step, let us write like this: cardinality of M, because bijection is there. Whenever we have a bijection between two sets, number of elements is same. That is the cardinality of this set HG, set that G belongs to G, right? So that is n equals to index of H in G, which is nothing but order of G upon order of H, because G is a finite group. So this implies what is order of G? Or let us write this first. So n times order of H. Order of H comes this side, which is order of G. And what is order of G? P power alpha M. So P power alpha M, right? And we know that how many powers divide order of G? we know that. If you have forgotten, let me just scroll this. Yes, so order of G was this. This is, say, I said what we needed. And P power alpha plus R. M માં કેટલા પાવર ડિવાઈડ કરે છે? R ડિવાઈડ કરે છે. So alpha is already there. R also divides, P power R divides M. So that is extracted out. So P power alpha plus R divides the right hand side, which is order of G. We know that P power alpha plus R. P power alpha plus R divides order of G. And so P power alpha plus R also divides the left hand side. Left hand side is n times order of H. But what is the relation between powers of P and N? That also, see, we have written everything. Yes, there was one equivalence class said that P power alpha plus 1 R plus 1 does not divide the number of elements in equivalence class. That equivalence class we called it M. Suppose there are n elements, that means P power R plus 1 does not divide n. So that means but P power R plus 1 does not divide n. So that means from here there are alpha plus R powers should come from this product. આ લોકોને આટલું દેવું પડશે. n times order of H must give P power alpha plus R, but n can give maximum how much? n can give maximum R. R से तो बढ़ेगा नहीं n के P power R. You can extract only P power R maximum. That is the thing. We don't know exactly R or not. Maximum what is this? P power R divides m. So બાકીના alpha ક્યાં જવા જોઈએ? Because P power alpha R plus 1 does not divide n. So maximum is P power R coming from here. Maximum P power R. So remaining are P power alpha. So at least P power alpha should come from order of H. Whatever n is not able to give, that should come from order of H. And so hence, so then, but this, then therefore, I can write therefore P power alpha divides order of H. Because the product divides n, so total power should come from this product. But n has maximum R. P power R plus 1 certainly not divides n. Therefore alpha to at least our whatever the remaining it should be. So then hence we have P power R order of H is or P power alpha is less than equals to order of H. Right, because minimum to atla to chhe. So this is one case. Now we show that other way. Order of H is greater than equals to P power alpha. Yeah, so what is H? Recall H. Let us recall H. What is H? H is all those G for which M1G equals to M1. All those G in the groups for which M1G equals to M1. So H equals to all those G in G such that M1G equals to M1. So if I take an element M in M1 and if I take an element G in H, then what is the product? So then this implies M1G same house. M1G, M in M1 and G in H. G in H, so the M1G equals to M1. So that means M1G belongs to M1. Right? So that means for every element M in M1, I take any element of H. So this set, what is this? This is MG such that G belongs to H. Right? G belongs to H. MG. So what is the product? Because if G belongs to H and M belongs to M1, then the product is going to be in M1. So this is subset of M1. Is it clear? Once again, what is H? H is all those elements of group for which G in G such that M1G equals to M1. So that means if I take any element here in M1 and I multiply with an element in G, so that G in H, then the answer also must be in M1. So that's M1G is in M1. So now this is true for all G. As it is true for all M1, it is, so M1 I keep fixed, M I keep fixed, but here I write this is true for all G in H. So here I write H. So MH, that means MG such that G belongs to H. So whenever this is there, this is going to be in M1. So this is subset of M1. I hope this is clear. The same thing I am writing here. Let me remove this explanation part. It is not going. Yeah. Okay, so note that for any m in M1, MH is subset of M1. Therefore, order of MH, number of elements here, is less than equals to number of elements in M1. Right? But what is order of MH? H is subgroup, M is also an element. So this implies order of H is same as these two are same. Right? This is less than equals to what is order of M1? ये सब किसके elements है? ये M1 and all this are. Whose elements are this? M1, M2. These are elements in the equivalence class. Equivalence class किसका है? Equivalence class is equivalence class of M. All these are equivalence class M in M. What is M? M is a collection of all subsets of G having exactly p power alpha elements. So M1 માં કેટલા elements હશે? How many elements will be there in M1? It is p power alpha. Right? Since order of H equals to order of MH. If you have any doubt, you can prove this, verify this. And order of M1 equals to p power alpha. So what we have here is order of H is less than equals to p power alpha, and hence I write hence order of H equals to p power alpha. Let us call it by 1 and 2. This is 2 for us. This should be 1 for us. Okay, so H is a subgroup of order p power alpha. This is what we wanted to prove. And this completes the proof, except that we have to verify all these things. So if you are good at verification, you think that you are good at verification, I'm not suggesting you to skip this. I am suggesting you to verify on your own. Skip કરશો તો બધું એવું જ લાગે, હા મને તો બધું આવડે છે એવું લાગશે. So I am going to verify, but this video will be longer from now onwards. All those steps I am going to verify. Do not look. I suggest stop this video right now, pause this, check all those verifications on your own, and then see if you are making a mistake. You can see. Okay, so I'll now verify all these other steps. So the proof is complete here. Now we'll fill the gaps. Okay, so equivalence relation. So let us make some space for our equivalence relation. Yes, I think this much space would suffice. Equivalence relation so verify so reflexive, right? So all this we have to show that M1 is related to M1. So clearly this is clear. M1 equals to M1E, where E is identity. So this is reflexive. Now what about symmetry? Relation is symmetric. How do we show? Suppose we are given M1 is related to M2, then we have to show that M2 is related to M1. So we are given this. So since M1 is related to M2, there exists G in G such that M1 equals to M2G. This was the relation. M1 is related to M2, then M1 there is G such that M1 equals to M2G. Now from this, how do we write? So therefore then M2 can be written as M1 G inverse multiplied by G inverse, both sides on the right. So this will be M1 G inverse equals to M2. So this is what I have written here. So that means this implies M2 is related to M1. So the relation is symmetric. And finally, transitivity. transitive. So for transitive, what we need, we are given M1 is related to M2 and M2 is related to M3, let us say. So we have to show that M1 is related to M3. So since M1 is related to M2, do we have space in the next page? I suppose not. થોડીક જગ્યા તો કરવી પડશે કદાચ જરૂર પડે તો. Let us bring this here. I can oh, yeah, fine. And these people can come. Yeah, this will be enough, I think. Yes. Okay, so since M1 is related to M2, there exists G in G such that M1 equals to M2G. Similarly, M2 is related to M3 implies there exists, let us say, H in G such that M2 equals to M3G. Right. So now, what is M1? M1 equals to M2G, but M2 is M3H here. M3H. Okay. Anamate H. Right. So M1 equals to M2G, and M2 is what? So M2 is M3HG. So we have M3HG. HG belongs to G. So M1 equals to M3 times some element in G. So that means M1 is, so that this implies M1 is related to M3. Relation is transitive. Yes. So very easy all this verification. Step 2 already we have verified. Step 3, H is a subgroup. So clearly H is non-empty. Why? Because E belongs to H, as E belongs to H. So because M1E equals to M1, this is true. So E belongs to H. H is non-empty. Now we show that H is closed under product. So let G and H belongs to H. So that means then M1G equals to M1 and M1H equals to M1. What we have to show, product also belongs to H. So now, so this is non-empty, this is product. So now what is M1GH? Product liye to this is M1GH, but M1G equals to M1. So this is M1H, again M1H equals to M1. So thus I can say that GH, so M1GH equals to M1 થઈ ગયું ને, M1GH also equals to M1 here, M1GH equals to M1. So that means GH also belongs to this H. So H is closed in the product. Now what about the inverse? So now let G belongs to H. So then what we have, M1G equals to M1 by definition of H. So now multiply by G inverse. So then therefore M1 G inverse equals to M1 G inverse. I multiply by G inverse on the right side, both sides. So there, that is M1. So this will become M1, and what will be on the right hand side? M1 G inverse. So M1 G inverse equals to M1. So that means M1 G inverse equals to M1. If this happens, so thus G inverse also belongs to H. So hence H is a subgroup. hence H is subgroup of G. Very easy verification, yes. So this is how you should be preparing for also exam if you want. Just remember steps. But if you are good at doing this, if you are regularly doing all these computations, then you can do. But if you just read the theorem, see the calculation, seeing the calculation will not make you an expert in doing calculation. So says H is a subgroup of G. Now what is remaining? Yes, this one. We have to show that this map is a bijection. So let us bijection and also well defined is let us is a well defined bijection. So 1 1 and well defined will shoot that in just one bullet, both birds. So if you want to show well defined, or yeah, so what we do, or you can start with 1 1 also, it is same thing. So if you want to show well defined, if two elements are same, then their image also must be same. So let M1G. So what we write here, we write like M1G and equals to M1H. This is how we write. Right? So, but exam માં ઘણી વાર કેવું થઈ જાય છે, what you do is this, you change this itself. See, elements are changing. Here the element M1 is fixed, and we are writing this as M1G, M1H and all. But sometimes what some people do in exam, I have seen this is M1G and they write M2G. G remains same and then this all. Here it is an equivalence relation, so it is fine. It makes sense, but otherwise sometimes it does not make sense also. So M1G and M1H be in the equivalence class. This now M1G equals to M1H. This implies uh, M1 GH inverse equals to M1. But what is definition of H? We have just proved that H is subgroup. M1G equals to M1, such G will belongs to H. M1G equals to M1. So here M1 GH inverse equals to M1. So this means that GH inverse belongs to H by definition of H. So GH inverse belongs to H. That means GH inverse or HG right coset. So thus GH inverse no right coset will be H. So that this means HG equals to HH. Okay, H does not mean that H આની અંદર આવે છે. I have just used notation. I could have taken G1, G2, but this is fine. HG equals to HH. This, but HG is what? HG is psi of here, psi of M1G. This is equals to psi of M1H. And if you go the other way, you have 1 1, the same thing, right? So this way is well defined. And if we go this way, what we have shown is it is 1 1. Right now we have to show it is onto. So now onto. For psi is onto, what we have to show? Onto is very clear. Psi is onto. Onto means we take an element here. So we have to take right cosets of right coset of H in G. As soon as we have a right coset, we have G. So let HG belongs to. Okay, so let me write HG dash belongs to. So it does not look like same. Or G in yeah, G in G, yes. So let HG dash be some right coset. Be some right coset. So this be some right coset of H in G. But then once we have G dash, so G dash બનાવીએ તો શું થશે? Then what is M1G dash? M1G dash is an element of M. Why? Because M1G dash, if I call it this as M, this is equivalent to M1. by definition. So let us not go in deep. But m1 g dash, it's an element of g dash is an element of g. So m1 g dash is equivalent to m1 by definition of equivalence relation. So m1 is in m, so it is in the domain. And what about we apply psi? And what about psi of m1 g dash equals to h g dash? So that the psi is onto. Yeah, this verifies the entire this, and this completes the proof of theorem along with the calculations. I hope this is clear. You just go back and see once more. If there is any difficulty, we'll discuss in the class or maybe in the tutorial session.